This afternoon is, let me find the slide here, Akash Prasad talking about parallel high-performance statistical bootstrapping in Python.
Thank you. Hello. Is this too loud? Okay. My name is Akash Prasad, and I am an undergraduate researcher in the Parallel Computing Lab at UC Berkeley. My talk today is on parallel high-performance bootstrapping in Python. To start with, bootstrapping is a general statistical technique that is used to determine the quality of a statistical estimator. It falls under the class of resampling algorithms and is useful when you have empirical data from an unknown distribution. A common task domain experts face is performing statistical analysis of data to estimate a statistic from a sample distribution. Because you often don't know the true distribution of the data, it is useful to know how reliable your estimate of the statistic is. Bootstrapping is a robust means to determine a confidence interval for your statistic, indicating how robust your estimator is. One of the shortcomings with the general bootstrap algorithm is it is not well suited for large data sets as it's not easily parallelizable. Fortunately, there is another method for bootstrapping called the bag of little bootstraps algorithm, or BLB. BLB was developed last year by Michael Jordan's machine learning group in the Berkeley AMP Lab. It is a new algorithm that serves the same purpose as the general bootstrap, but it relies on statistical subsampling to reduce the size of the problem while still producing accurate and statistically robust results. Furthermore, because of its structure, it is easy to parallelize, and this makes the algorithm conducive to using on very large data sets in distributed environments. The BLB algorithm opens up a range of applications that were previously impractical given the computational properties of the general bootstrap. Some problems that BLB can be applied to include common tasks like evaluating a machine learning model, determining the quality of a linear estimator, and performing hypothesis testing, which is a common task in statistics. These are common problems that domain experts face, and given that scientific data is growing faster than the rate of single-core processor speedup, it would be useful to have a highly parallel and optimized implementation of the BLB algorithm. Many domain experts who will benefit from using the BLB algorithm are productivity programmers, and historically, parallel programming has been difficult for productivity programmers who are often not specialists in parallel programming frameworks and techniques. Furthermore, the methods available to harness parallel hardware platforms become increasingly specialized in order to expose maximum efficiency to efficiency programmers. So one way to bridge this disparity is through a combination of code generation, code lowering, and just-in-time compilation techniques called CJITs, which stands for Selective Embedded Just-in-Time Specialization. CJITs provides the best of both productivity programming and efficiency programming by allowing a compact domain-specific embedded language, or DSEL, to be embedded in Python. It allows us to create a mini runtime compiler for a particular DSEL, which itself is implemented in Python. This mini compiler, called a specializer, performs code generation at runtime, allowing productivity programmers to express their problem in the appropriate DSEL, and allows them to harness the performance and parallelism benefits of using lower-level languages. There's a CJITs framework called ASP, which stands for ASP is CJITs for Python. ASP is a powerful framework that allows us to bring parallel performance to Python using targeted just-in-time code generation. It provides an interface which allows multiple applications to be built and run upon multiple parallel frameworks by using a single specializer. Each specializer contains tools to translate functions written in Python into equivalent functions written in low-level efficiency languages. So we use the ASP framework to create a specializer for the BLB algorithm in order to enable productivity programmers to take advantage of a high performance and parallel implementation of BLB. Productivity programmers using the specializer can write the statistic functions they want assessed in Python, and then their input functions will be lowered by our specializer to efficiency level code, in our case, C++. In order to do this, we had to first define a DSEL for the BLB algorithm. So a BLB problem can be described by the estimators it uses, its sampling parameters, and its input data. We designed the DSEL to concisely express the most common features of BLB estimator computations, specifically iterating over large data sets and doing dense linear algebra. Because BLB problems often deal with high-dimensional data, an important feature of this DSEL is the ability to express vector operations. The sampling parameters and input data parts of the problem are not part of the DSEL, as they're simply patched in when the specializer is initialized. So on the right, there's an example code block that initializes the BLB specializer with a problem instance. Using just these two dozen lines of code, you can initialize and run a BLB specializer to perform model verification on, this was 100,000 emails. So we are trying to evaluate the classifier's accuracy. So the compute estimate method classifies the input emails into folders, and then the other input functions work to determine the accuracy of these classifications. So our BLB specializer combines various tools, namely the ASP framework and a few thousand lines of custom code, to inspect and lower Python code at runtime. The specializer allows the domain expert to easily express BLB computations, which can be difficult to write in an efficiency layer language. Though the specializer converts most of the Python code as provided to C++, certain constructs, such as loops over the input data, are detected and rewritten in an optimized way when they are lowered to efficiency code. The specializer is also able to make optimization decisions based on the input parameters and platform capabilities. So it is source and performance portable. So our BLB specializer is equipped to make two pattern-level optimizations. These optimizations change the steps of the execution pattern, but do not actually affect the user's code. The first optimization is our specializer decides whether or not to load in subsamples of the data. These subsamples are arrays of pointers, so they can be accessed by indirection to individual elements, or they can be loaded into a new buffer. Loading in these subsamples encourages caching and can lead to performance gains of up to 3x for some problems and platform combinations. However, as the data size grows and the time spent moving data and contending for shared resources outweighs caching benefits, because the specializer knows about the platform and the BLB inputs, it is able to determine whether or not to load in subsamples based on the size of the subsamples as well as the size of the L2 cache on the platform. Another pattern-level optimization is choosing the sampling parameters for BLB. These determine the efficiency versus accuracy trade-off of running the algorithm. These parameters can be specified by the specializer user and are not adjusted based on platform parameters because the specializer does not include a method to determine acceptable losses and accuracy. So in order to evaluate our BLB specializer, we designed an experiment to determine the accuracy of a machine learning model using BLB. We trained the model, specifically a support vector machine classifier, on a publicly available data set containing over 1 million internal emails from the Enron scandal. We extracted features from 126,000 emails using Bag of Words model and trained our model on 10% of this data to classify emails into folders they were assigned to by the recipient. We then applied BLB to the remainder of this data to determine how accurate our model was. So just to give you an idea of the size of the data, each feature vector contained 96,000 features, each 1 byte. So the size of the data set was over 10 gigabytes. We used this experiment to evaluate our specializer for both performance and accuracy. As you can see in the strong scaling graph on the right, we got fairly good strong scaling results, actually almost got linear scaling. So by using 32 hardware threads, our specializer achieved a speed up of 31.6x. So using 32 hardware threads, we computed the accuracy of the machine learning model in 110 seconds on over 10 gigabytes of data, whereas a serial version took over 3,500 seconds. Furthermore, we benchmark our result against other methods of machine learning model verification and determined that our results were accurate. To summarize, we built a CJIT specializer for the BLB algorithm, which allows domain experts to quickly and accurately perform statistical bootstrapping on large data sets. We used our specializer to determine the quality of a machine learning model and got favorable results, both in terms of accuracy and performance. Currently, our specializer supports OpenMP and Silk backends, and we hope to add support for GPUs through CUDA, and in addition, a cloud version which is currently being constructed in order to support even larger data sets in the range of terabytes. Our BLB specializer is part of a growing family of CGIS specializers, many of which are already in use. We have a paper in the proceedings of this conference, the same title as this talk, High Performance Parallel Bootstrapping in Python, which has more details on our specializer and our experiment. Furthermore, the BLB specializer is available for public use on cgits.org, along with the other CGIS specializers. All right, thank you.
Questions? And if you want to use questions, you go use the mic over there.
Well, first, where is that lovely scene?
I'm not sure. I think it's a standard Mac background.
Okay. What are some uses that you can see this being put to in more practical terms?
So there are already a lot of uses for statistical bootstrapping, but BLB allows you to open up, to use this on very large data sets in tens or hundreds of gigabytes or even terabytes. So things like verifying machine learning models, estimating or determining the robustness of linear estimators or other statistical estimators, and doing hypothesis testing in statistics.
All right, let's thank our speaker again.